Welcome to Wireless Future. This is episode 23 and I'm Emil Björnsson. I'm located in Stockholm today. And at another location we have Erik Larsson. Where are you today?
Oh, good morning, Emil. I'm at Linköping as always. How are you this morning?
I'm great. It's a rainy day, but I'm inside. And then we have a third person on this call. We have a guest. I guess you are in Gothenburg. So Professor Henk Wymeersch from Chalmers Technical University, and you're professor there in communication systems, right? How are you today?
Yes. Hi, good morning, Emil. Good morning, Erik. Yes, I'm very good, thank you. It's indeed raining here in Gothenburg as usual.
It's great to have you here. And the reason that we invited you was particularly to talk about localization, which I know is one of your expertise. And I was just localizing each of us to the nearest city, but I was thinking that probably we can, with wireless technology today and in the future, localize people to a much higher accuracy. So let's kick off the conversation. What is wireless localization? Is this the same thing as positioning?
Right, so these terms are often confused, and I think rightly so. To my understanding, they mean exactly the same thing, but they come from different fields. So the terminology of positioning comes really from the radio world, especially 3GPP, and refers to the determination of the 3D or 2D position of a connected device, like a smartphone, let's say. While localization originally came more from the robotics community, where it really referred to localizing a robot in 3D or even more dimensions in a map that it would build itself. But I think from the point of view of localization from radio signals, they really mean the same thing.
Yeah, so we might be using the terms interchangeably here, I suppose. In fact, as you might know, I worked on localization and positioning for a brief period of time at the end of the 90s. And when I told people what I'm doing, working on positioning, they thought I was working on like positioning products in the market, which is a different thing, right? So maybe localization is like, I don't know, more an ambiguous term perhaps for the layman, I'm not sure. In any case, I thought we could start a bit on a historical perspective, because if we think localization, then, I mean, GPS, for example, has been around for many decades, right? And cellular positioning has been around for, I suppose, well, at least 20 years, say. So now, during the last 20 years, to my understanding, what has happened is that, well, the signal processing has improved a lot, right? I mean, like, for example, mobile phones and handsets are a lot more capable. And also, GPS has evolved into network-assisted GPS, where, say, the handset uses combined signals from the cellular network and satellites to position. And also another thing that has been invented and made reality in the last decade or so is the integration with IMUs and accelerometers and magnetometers and other types of sensors in the handsets, right? So are we now reaching like the end here, or is there a need for more research on this field, or where do you see this like heading in a historical perspective?
Yeah, so historically, as you say, I would say GPS was kind of a landmark development where you could localize almost anywhere on Earth in 3D. And then, the connection with network-assisted GPS, where you get assistance information to improve the localization, the fusion with additional sensors like IMU, inertial navigation, all of this kind of really helped push localization and performance. But at the same time, GPS doesn't work everywhere. So you can imagine when you're in a city with tall buildings, then many GPS satellites will be occluded, and they don't have a good geometry for you to localize. So then you need other technologies. And this is in particular where other radio technologies can help you a lot, such as ultra-wideband, as also the 4G, 5G signals. And the need, I think, is driven in two directions. One is the use cases. So that there's a push for additional use cases that need higher and higher accuracy for localization. And on the other hand, there's the development of the technologies which enable better and better localization, which then in turn create new use cases. So it's a kind of self-fulfilling prophecy in a way.
Yeah, of course. I mean, I suppose once there is a technology available that can offer us something, then there will be use cases and applications, right? And it's quite amazing, I think, how like accuracy of positioning or localization systems, even, I mean, you just open your cell phone and open the maps, then how that has improved over the last few years. And I suppose that it is this integration that you mentioned of GPS on one hand and cellular signals on the other hand, and the way that they can interact and help and support each other that has made this possible to a large extent.
Yes, I fully agree. But nevertheless, the accuracy that you get is maybe down to a few meters in typical cases, unless you have very sophisticated processing. And for novel use cases in the coming years, this is probably not sufficient. You can think of autonomous driving or localizing of UAVs.
So I was thinking that in this episode we will talk about some of the technology aspects and what process needs to be done in order to position or localize something, and maybe give a hint about what we then could improve in the future in order to bring down the error margins in your localization. So if we start with just the simplest case, some kind of line of sight where you have a radio transmitter and you have your object you would like to communicate with or to localize in one or the other direction. How does localization work in the line of sight scenario?
So the basic way of operating, which is common also to GPS and also to cellular localization, is something called time difference of arrival, where you have several base stations or GPS satellites that are synchronized and that have known positions. And this aspect of synchronization is really important because the way that you measure distances, let's say, is through time, the travel time of the radio signal over the air, and then related to the speed of light, of course. And that means you need extremely tight synchronization to assign meaning to those measurements. Anyway, so what would happen typically is that those base stations or satellites, they broadcast signals. These signals are orthogonal in some way so that the user can disentangle them and figure out which signal comes from which base station or satellite, and then just measures the time of arrival of that signal. So it locally checks for some kind of correlation peak and says, okay, this is when the signal arrived in my own frame of reference, in my own clock. And then if you, for instance, want to do 3D localization, you need 4 base stations or 4 satellites to localize because you want to solve for 4 unknowns, the 3D position and the 1D clock bias. So this is the basic operation under line of sight.
So these are the basic operations in line of sight. So if we think like fundamentally, what is it, or what factors affect the accuracy that we can get in a positioning system? I mean, I would think, for example, that received power or received signal to noise ratio would make a difference, right? And that the bandwidth of the signal would help, and or rather that the large bandwidth would help, and that the more antennas you have, the better resolution that you can get. Could you comment on that, or is there like anything else that any other determining factors in terms of accuracy? Now, staying with the line of sight, perhaps for the sake of the example here.
Right. So I think we should distinguish probably resolution versus accuracy. So these are not the same thing. So resolution refers to the ability to distinguish 2 signal paths that are relatively similar. And then you have resolution in the delay domain, resolution in velocity, resolution angle of arrival, angle of departure. So there's many domains in which you could resolve multipath. So you can imagine that 2 signals are coming from the same direction, but with different delays. And if you have sufficient bandwidth, then you can resolve them in the delay domain, even if you cannot resolve them in the angle domain. Similarly, if you have enough time to process your data, you can have good Doppler resolution. So you can distinguish signals that are coming at same distance with same angle but different velocity if you have enough time to process your signal. Similarly, for instance, angle of arrival, resolution depends on the aperture of the receive array. So if you have a large array with many antenna elements, then you can distinguish signals with slightly different angle of arrival. And finally, you also have angle of departure resolution, which depends on the size of the transmit array. So all of these tell you how well you can separate, let's say, the line of sight path from all the other paths. Once you have this resolution, then it's about accuracy. And accuracy, like you say, Eric, is really about SNR. That tells you how well can I estimate the time of arrival or angle of arrival of this one particular path. And while resolution is something fixed, given the system, right, the accuracy is in principle unbounded. It just depends on the SNR that you have.
Great. So if we then compare the localization problem with communication, I guess we are using sort of the same wireless medium around us. And I know communication also is, there the signal to noise ratio is an important metric in order to determine how many bits per second we can communicate. But are these two use cases of wireless technology using the channel in the same way? Is it the same properties that are important to get a good performance?
Yeah, I would probably say not at all. And in fact, coming from a communication background and moving into localization, I see there's really a big gap between how communication people and localization people treat the channel, what they know about the channel, what their models are, even though physically it's exactly the same channel, of course. So there's a number of differences. So first of all, in localization, you don't care about data because you're sending pilots. So the thing that you care most about is really the parameters of the channel, the delays and angles that are present in the channel, or the geometric information in the channel. While for communication, you care about your data, and estimating the channel is just something that you need to do to get to your data. So this is really something substantially different. Also, in localization, you care, as I said, about this resolvability, about having a clean line of sight path, while for communication, maybe this is not even very desirable, that everything is very well separated. You care maybe about rich scattering environments with lots of diversity. From a localization perspective, I don't want that at all. I want to have a clean separation of the different paths. And also, if there's a very weak multipath component, from a communication point of view, you would just discard it. You wouldn't care about it. But for localization, this could be very useful because it carries geometric information. So there's a big gap between those two approaches, communication versus localization.
It's really like in localization, then it is the channel or the estimate of the channel that contains the information, right? Whereas in communications, the channel itself is of no independent interest. It's almost like just a nuisance parameter when you are to detect your data.
Yes and no. I think this is somewhat changing in the sense that as we move to 5G and higher carrier frequencies, that the location information can become important for the communication. You can think, for instance, of beam alignment, where having prior location knowledge can really help speed up the initial beam alignment problem.
Right, that's a good point indeed. So speaking of waveforms, are there any particular waveforms that are good for localization? I mean, I would think, for example, that one thing we know is that waveforms that are good for communications, they tend to have a wide bandwidth, right, and a relatively flat, say, spectrum with about as much power at every frequency. And waveforms that are good for localization, if you think, for example, Kramerov bound for time delay estimation, then it's also the effective bandwidth they want to be large, right? And so signals with a wide spectrum support and that have a wide bandwidth should be good both for communications and for localization. But beyond that, say elementary insight, what can be said about what waveforms are suitable for localization?
Yeah, so here, again, I would think resolution versus accuracy. If I think about resolution, then it's really just, okay, the bandwidth that I have available, coherent integration time, aperture of the transmit and receive array. It doesn't really matter what kind of waveform that I use. But if I think about accuracy and Kramer-Rao bound, then indeed it matters a lot. So a good example would be, for instance, as you say, in a wideband signal, let's say OFDM, you would want to have a maybe uniform spectrum, while for localization you want to put more power on the boundaries of the spectrum. And something similar happens, for instance, for beam design. So suppose that you want to send information towards a user in a certain direction, you would direct a beam towards that direction. But for localization, this turns out to be not the optimal thing. You want to send a combination of beams that are directive, plus that have a null towards that direction, because this combination helps you to do better localization. So the design is somehow different.
Yeah, I mean, it's not only the camera bound that matters, right? It's the ambiguity function of the waveform, of course. And then there might be cases where it's advantageous to, rather than spreading the power, say, uniformly over some frequency band, you want to put a lot of power at the end, at the left and at the right end of the spectrum, and just a little bit in the middle. Which will give you a good camera bound for accuracy, but it'll also give you a reasonable, you need something in the middle of the spectrum to get a reasonable ambiguity function.
Yes, and here there's again a distinction between kind of localization without any prior information versus a tracking problem. So when you're doing tracking, then you already have lots of prior knowledge of where the user is, and then you could use this Kramer bound optimized waveforms because you don't care about the ambiguities. But if you know nothing, then of course ambiguity function should really be taken into account in the design.
So now you have been using some terms here that I'm not sure if all of our listeners are familiar with. So just for a brief recap, so the Kramer bound and the ambiguity functions, what are these things? This is signal processing terminology, I suppose.
Yes, so the Kramer lower bound is a way to, it's a lower bound on the accuracy of estimation problems under some technical conditions. So it basically tells you, given this setup, this is the best that you can hope to achieve. And then if you have an algorithm that operates close to this bound, then you're basically done. There's no need to do better. Then you think about reducing complexity. And so this is a tool that is often used for designing signals, for deciding where you should put base stations, how should satellites be distributed, how you do time frequency and spatial allocation of signals. The ambiguity function, you can think about autocorrelation function. So I think that's really what this is about, that it should have like a distinct peak and no distinct side peaks, no significant side peaks, because these would be mixed up with the true location of the objects.
Great. So we have these generations of cellular technology, and I think most people, when they hear about 3G, 4G, 5G, they think about the communication benefits that you're having, maybe higher data rates or lower latencies and things like that. Then I read in a recent paper of you where you were describing sort of how the wireless localization technology has sort of evolved from generation to generation. You talked about 4G, what happens now with 5G, and then wrote about what might happen beyond 5G as well. So I was thinking we could go through this evolution and then start with how would you say that localization works in 4G? So
in 4G, the main reason to do localization, and this is important too, is for emergency call localization. So there was no commercial use case for localization. And the requirement on the localization accuracy was not very strict. The way that localization is done in 4G mainly is something called OTDOA, and this is basically TDOA like I explained before, so where base stations send signal in the downlink, the user estimates the arrival times, and from this constructs basically hyperboloids, and then on the intersection of those the user must lie. This is limited mainly by the resolution, which is the bandwidth, right? The bandwidth is small in 4G, which means that you have uncertainties of the user location on the order of 50 to 100 meters.
Okay, so
Yeah, so I mean, speaking of generations here, right, and how the technology actually works, like in our mobile phones, then how does positioning work? If I pick up my cell phone here, okay, and open the maps, say, app on it, then what happens behind the scenes there? What signals are used and how are they fused, and how does this differ from whether I have a 4G phone, say, and a 5G enabled phone?
But the position estimate that you get on your phone is a fusion of many sensors, right? It's not just the radio signal. So there's the GNSS information, there's maybe IMU information, other kind of fingerprinting information that could be available in the system. And then in addition, you could have this very coarse 4G information. But I think if you have a 4G phone and you want to localize yourself, probably the 4G signal does not play a very important role. Not to get this very precise location.
Not to get the precise location, but does it not even play a role in order to help the GPS? I mean, one of the functions in a GPS receiver is to locate the peak of the correlation between the spreading code and the received signal from the satellite, right? And when you do that, then there might be spurious peaks due to noise. So the more prior information you have about where the peak is expected to be, the better you can do, and the less sensitive to noise and maybe even interference you can be in the localization. So I think that's what's called the network assisted GPS, right? That you're using side information from the cellular network in detecting the satellite signals in GPS and in estimating their time delay, which is then subsequently used to obtain the position fix. So is that being done? I mean, is that technology now widespread and implemented in our handsets with network-assisted GPS so that the 4G, say, or even 5G signals help the mobile to, coarsely locate where this correlation peak is and thereby help the GPS in tough operating conditions? I mean, for example, sitting in a basement or at the cell or at some place where satellite coverage is very poor, then this should be highly useful, huh?
Yes, I agree in principle it should be highly useful. Whether it is used a lot, I'm not really sure. I don't have information regarding that.
So I remember, maybe it was almost 10 years ago now, that I wanted to track my running times and things like that. So I bought a Garmin GPS clock, and I realized that where I was living with tall buildings and a hill next to me, it was very hard to sort of lock onto sufficient number of satellites to get a good starting point for my run. So I thought that I was somewhere completely else. So then I was like, oh, I bought this clock, and now maybe I should just use my phone instead, because at least it is pretending as if it knows where I am because of this assisted thing. So there it seemed to play a big difference for me.
Yeah, that's a good point, of course.
Yeah. So in 5G, you said that then the actual cellular signals are also used more directly for localization. But I mean, what is the basic accuracy that we could get in 5G, and is GPS still useful then? I mean, or in a 5G handset, is it it can receive GPS signals and it can receive 5G signals. Would the accuracy from GPS be comparable to the accuracy for 5G, or is it still essential, I mean, to combine the signals and to use also other sensory input from IMUs, for example?
Well, I think whatever will happen, you will always fuse information from different sensors. I think that's good.
So that's really key here to the improved and in fact the quite amazing accuracy that we can get from, I mean, off the shelf, like cell phone equipment, right?
Right, but then in 5G, of course, we will have these new frequency bands, FR2 range, around 28 gigahertz, where there's a lot of spectrum available, a lot of bandwidth available, and this is expected to really improve positioning.
So and that then goes back to the things you mentioned before, then, yeah, more bandwidth is better, and then if you go up in frequency, you also, do you get better angular resolution and things like that as well?
Right, so in 5G is the first generation where they said, okay, probably we can also support some more commercial use cases, not just this emergency call localization. We can really push positioning performance. And then they've spent a lot of effort in 3GPP to define new reference signals, new methods for localization. So it goes far beyond time difference of arrival localization. There's also round-trip time measurements, so from a base station to a user and back. And then, as you say, Emil, there's also angle measurements, so that where the base station would send beams in different direction, the user measures power, and then the beam with the largest power would then give an angle of departure estimate, which can really help localization.
So one term that I hear sometimes, in particular when people talk about future technologies and in keynotes and so, are sensing. Is this related to localization as well?
It depends who you talk to, but in my view, yes. So there's different kinds of sensing. There's something called monostatic sensing, and there's also bistatic and multistatic sensing. So monostatic sensing is what happens in your the radar of your car. right? So the sensor emits a signal, you receive the backscattered signal at the same sensor, and then you can map the environment. In 4G, 5G systems, this is relatively hard to do because you need full duplex operation. And this is full duplex where you need an enormous kind of isolation with the transmitter and receiver chain to receive those very weak backscattered signals. So this is really hard to achieve. There's a lot of academic studies there, but in reality, this is really challenging. There's also then bistatic sensing, where the transmitter and the receiver are not located in the same place. And then you can imagine the case where there's a base station emitting a signal, a user is receiving the signal, and also trying to detect the multipath and try to relate the multipath to objects in the environment and then map the environment. This would be bistatic sensing. In addition, there's also other sensing, like weather sensing, rain sensing, that could also be done by radio signals.
So when you say, I mean, when we say localization or positioning, we really mean, I thought, obtaining a coordinate, right, of your well, whatever device you're having. But when we say sensing, it's more about learning something about what the environment looks like. For example, if you're on the highway and you have a radar device mounted on the car, and figuring out whether there's anyone ahead of you or anyone to the side or to the left and the right and so forth. And it seems to me that well, everything that makes like a waveform or a system good for localization should also open opportunities for sensing, right? I mean, the larger bandwidth you have, for example, the more finely you can resolve paths in range, and the larger aperture, the more antennas you have, the more resolution you'll have in the spatial domain and so forth.
Yes, so maybe I can comment on that. This is exactly true, but I don't see them as two separate problems. There's not a localization and a sensing problem. They really go hand in hand. And this is known as something as SLAM, simultaneous localization and mapping. The example that I gave before, I think, is a good one, where you can localize with a single base station if you also exploit the multipath information. If you don't exploit the multipath, you are lost.
So with SLAM, you actually build a map simultaneously as you proceed along and locate or position yourself.
Indeed, yes.
So now looking ahead, I mean, so for 6G, there are a number of, I think, new technologies emerging, right? I mean, there is terahertz for one thing, and there's also this concept of reflecting intelligent surface, which is essentially like a passive MIMO base station, right? Where you have some kind of panel with many small elements, and these elements can be individually configured so that an impinging radio wave is reflected into some direction that you can adaptively decide. So how do you see that terahertz and reflecting intelligent surfaces will or could play a role in improved, say, localization and also sensing, for that matter, in 6G?
Yeah, so the technologies that you list, these intelligent surfaces and terahertz carriers, are indeed really interesting for communication, but I think also even more perhaps for localization and sensing. But when I talk about terahertz, I maybe mean carriers up to 300 gigahertz, maybe not all the way to terahertz, just because the range will be really small at those high frequencies. And the main benefit is, again, and it really boils down to these essentials, right? It's about resolution. Because we're going to terahertz, because when we want to push the data rates, the only way we can push the data rates is by larger bandwidths. And again, this is really good for localization. The intelligent surfaces, they act like base stations, somehow cheap base stations. And if you can localize them, if you know where they are, you know what their orientation is, they provide new signal sources for positioning. So you can localize with one base station. I think you can even localize without any base station just by using these intelligent surfaces. And in general, my view coming from localization is that we're kind of driven by what the communication people do. They come up with all these amazing concepts. I mean, think of massive MIMO, millimeter wave, now terahertz, intelligent surfaces. And then we think, okay, how can we reuse those for localization? How do the models of these technologies need to be refined, that they contain geometric information that we can extract?
Right, so you're saying that with terahertz, then we'll get these enormous bandwidths, which in turn will give us this very fine time and range resolution. And with intelligent surfaces, then, well, in principle, they could be like configured to provide additional multipath that could be exploited by localization algorithms. Well, so these are quite exciting prospects, I think, and seems like a gold mine of research problems for folks to work on here for the decade to come.
Yes, indeed. And I've been working in the field of radio localization since, I would say, 2005, and it was kind of a very small area, right? But now, at the end of 5G and the beginning of 6G, it became this enormous boom where the communication community sees this need for tightly integrating communication, localization, sensing, and all of these things are converging. So it's a really exciting time in this field.
Yeah, and it seems also that we might be having larger improvements that people really can experience in their everyday life in this area, because if you now can deliver with 5G 500 megabits per second, the number of situations where you need more than that might be rather slim. Then you can definitely find special use cases for it. But if you are going from being able to localize something down to tenth of meters to I don't know, how accurate can you get the estimate, you think, in a 5G system, so millimeter wave and everything?
Yeah, there's a distinction between, I guess, what people predicted and what is really possible. If you look even at 3GPP documents, they predict very accurate localization indoors, line of sight, under synchronized conditions, down to a few decimeters. Whether this is really possible depends on lots of other factors than just the pure signals. It's also about hardware impairments, calibration effects. I think people are now stepping back from that and maybe thinking 5G will go down to a few meters, right? Maybe 2-3 meters. Well, 6G will be the amazing new technology that will bring us down all the way to 1 centimeter. But if you ask me again in a few years, then I say, of course, 6G could not deliver, and maybe it was 20 centimeters. But no matter what, it would still be amazing.
Yeah, we are always aiming for a little bit more than we can deliver, and then we promise that 5G will solve everything until 5G appears, and then 6G is the new technology that will solve all the problems that 5G had, and maybe we are recycling the same visions, just a little bit more, super faster. One thing that you mentioned there was about hardware impairments. I was thinking here, I have my laptop in front of me, and it's like less than a meter from my Wi-Fi station. So I probably have a huge SNR, I don't know, 60 decibels or something. And then I'm really limited, not by the quality of the radio signal, but probably about what kind of radio hardware I have, because I cannot get larger modulations symbols or more constellation points than the standard is predicting. Do you think we will enter a case where it won't be the radio resources that are limiting our accuracy when it comes to localization, but rather the hardware in the different devices and how synchronized they are?
That's probably true, and not just for localization, also for communication. There's so many hardware impairments when you go to these terahertz, or at least hundreds of gigahertz carrier frequencies, that will be much more dominant than at centimeter wave or millimeter wave frequencies. Nevertheless, from a communication perspective, typically you care about this end-to-end channel, right? And you don't really care what happens in between. Well, for localization and sensing, we are much more sensitive to the hardware impairments, because we care exactly about these angles and delays and Dopplers that are hidden inside of the channel and that are really affected by all the processing that is done. Just think of phase noise, mutual coupling, power amplifier nonlinearity. They can just completely destroy the quality of our position estimates. So yes, I think this is an important challenge. A related challenge is also calibration, which I mentioned before. If you want to go down to 1 centimeter localization accuracy, right? 1 centimeter, if you think how much does light need to travel to cover 1 centimeter, it's a fraction of a nanosecond, which means that you need to be able to synchronize devices with this extreme accuracy, to synchronize base stations at the, picosecond level, to calibrate arrays individually to know the complex beam patterns, to place them exactly in the right orientation, is enormously challenging.
Yeah, so these are extraordinary challenges, as it seems to me. I mean, to calibrate an array with that precision, right? So it really sounds like at some point we'll be reaching a situation where hardware impairments and the ability to calibrate and compensate for nonlinearities and phase alignment errors and so forth will dictate ultimately what accuracy we can achieve. So speaking of technology and algorithms for localization, we talked a bit earlier, I think, about triangulation and trilateration, right? Where you have a line of sight propagation environment and you obtain your position essentially by measuring time of arrival or time difference of arrival or angle of arrival or angle of departure possibly. But what if we are in non-line of sight, so that there's a lot of multipath around and objects that scatter and reflect the signals? What are the state-of-the-art technologies there today?
Right. So this happens typically a lot, I would say, in lower frequencies, that you have rich scattering, lots of multipath, and non-resolved multipath. Because if the multipath can be resolved, then you can apply these SLAM techniques and kind of track and map the environment. So then you can localize even when the line of sight is not present. But in these lower frequencies, then I would say the state of the art is fingerprinting, which means that someone beforehand maps the environment, so goes in different locations and kind of measures the channel, and then builds a database of this mapping from channel to location. And then the user would come in later and then measures the channel, and then you would invert this mapping to find the best estimate of the user location. This is really the state of the art, and this of course closely relates to machine learning technologies.
Right. So what you're saying essentially is that once we have enough resolvability of the multipath components, which could be achieved, for example, by a large enough bandwidth and high enough SNR, then in principle we can track how individual multipath components appear and disappear and how they move around in the environment, right? So essentially using like a parametric or semi-parametric description of what the environment looks like. But in the regime where multipath isn't resolvable to any significant extent, which is typically the case at lower frequencies where also the bandwidths are less, then you'd rely on machine learning algorithms and specifically fingerprinting, which to my understanding is basically that, you send someone around and measure the channel impulse response at different locations, and then you create a database, and then you have an algorithm that, it receives an estimated channel impulse response, and then it goes to the database and looks where is it most likely that this came from, right?
I think that's exactly true. But nevertheless, even at higher frequencies, even when multipath is resolved, then there's a next level of unresolvability, right? Because even if a signal is coming from a certain wall, this wall has many features, will have many multipath components, diffuse multipath. And even there, when you think about, for instance, radar imaging systems, then machine learning also plays a role there to figure out more refined features. Is it the bicyclist or is it the pedestrian? What is really happening in this environment?
Yeah, one thing that seems to be true from radar is that once you increase your aperture or increase your bandwidth, what happens is you just discover more and more components, right? More and more scattering objects, more and more multipath and so forth. So it's not like you increase your bandwidth and, the multipath components stay the same. It's just you can resolve them better with finer accuracy. But in contrast, you discover more and more of them. So the environment really looks messy, right? No matter how many antennas, how large bandwidth, how high SNR, you're just uncovering more and more detail in your propagation environment. So at some point, it might still be machine learning that will come to the rescue here then.
Yeah, that's exactly true. And this is also what we're seeing in radar and other kind of sensors, that machine learning will be used at this kind of final processing step to reveal all the hidden information.
So I think one very basic type of fingerprinting that our mobile phone have been using for a long time is to just keep track on what Wi-Fi routers that are around. I remember a few years ago there were a big thing about that both Google and Apple have some kind of databases of what Wi-Fi station to have, and then they were sort of storing, at least Apple was storing forever, how you have been moving around with your phone and what Wi-Fi station you saw, so you can create maps of it. Then when that became public, they were sort of also starting to remove part of it. So it seems like fingerprinting is something that is actually used already.
Yes, I think so. Of course, it requires this continuous mapping effort and keeping track of building this database, which is a bit challenging. And as you somehow hinted at, there's also some potential privacy considerations there.
Indeed, I think that was sort of the news media coverage approach to it, that the privacy aspect of it. And to switch a bit topic, I was looking at your Google Scholar and saw a very impressive thing that you have one paper called Cooperative Localization for Wireless Network with more than 1,000 citations. That made me curious. What is cooperative localization?
So the principle of cooperative localization was to let devices exchange signals with each other and then compute relative positions, so distances, angles, Dopplers, and then aggregate all this information throughout the network. And then if you have a few devices that know where they are, then you can use this information to localize everybody in the network. And of course, this was the extreme case. You can also think of this as one device that's connected to a base station and then connected to another device, and they could help each other localize. So this is really what cooperative localization is about. So devices helping each other localize through relative measurements over, you can think a side link in a 5G system.
So is this something that is now on the way of being utilized in 5G or in future? Or where do we stand on this type of technology?
Yeah, in 5G it's a bit tricky because the telecom companies are not very keen to use those side links, because then maybe they lose some control. There are other applications you can think of, automotive radar systems that are will be used in the future to communicate as well, and their cooperative localization could play a role. So I don't think commercially it's been used, but I do see a potential in the future that it will be used, and I think it's getting ever more likely that it will be used.
Yeah, I think one interesting aspect that you were also touching upon there is to what extent localization is a service that should be in the network itself. It delivers it to you, and maybe you pay extra for the service or something, or whether it's sort of an app that runs over the top. I guess when you are using Google Maps or Apple Maps, you get localization estimates, but you also get some additional information from their servers, and there is some kind of gathered information, maybe not what you described, but that you know where traffic jams are going to happen because there is a database around this thing. So maybe this is something that can be added on top in some kind of cooperative localization apps.
Yeah, probably. I mean, all of this is about interfaces, APIs, and agreements between these industries. So once these measurements become available, then you can run lots of applications on top, indeed.
Mm. Yeah, quite amazing. Wow. So, yeah, I think we are approaching the close-up here, Emil. And one thing that I will bring back, and I think everyone in the audience should bring back, is that it seems that, positioning historically has been a lot about geometry, right? Obtaining time of arrival measurements and time difference of arrival, and drawing circles or hyperbolas and check whether they intersect and so forth. Whereas the kind of modern and emerging approach is really to use machine learning, right? Where everything's like data-driven, where you fingerprint your environment, you collect measurements of what your channel impulse response say looks like at different locations in the room or out there in nature. And then you create a huge database and just rely on that data for when you obtain your location information. It's quite exciting, I think, and an exciting prospect for how modern machine learning techniques also can be used. Is there anything else, Henk, that you would want to add here to the discussion before we close up for today?
Yeah, maybe one item I could mention is that I agree that machine learning has lots of uses, but maybe it should not be used to solve all problems. There's many problems that we can still use model-based methods, I think, for a few more years. At some point, machine learning will be needed. But one area where I see that machine learning could play a role is in dealing with the hardware impairments. Because when you have transmitter and receiver chains with the concatenation of many linear, nonlinear, and noisy impairments, it's impossible to build a model. And then using AI could do that.
I think, no question, I mean, we are in agreement here, and don't get me wrong. I mean, so I obviously also think that once we have models that are accurate enough, then we should exploit them, right? But I thought the point is rather that we said earlier that, I mean, you go up in aperture, right? You add more and more antennas, you get higher and higher spatial resolution. You go up in bandwidth so you can resolve more and more multipath components. But even so, it's difficult to build accurate geometric models that account for all the multipath propagation and all the scattering and all that's going on there. Because as we increase bandwidth, as we increase aperture or number of antennas, we just uncover more and more detail. So at some point, an entirely based or model-based approach to the positioning problem becomes just infeasible, and relying on machine learning might in the end be the only option.
Yes, indeed. But I guess time will tell.
Time will tell, yes.
So then before we wrap up, I hope we have inspired some people, our listeners, to want to conduct research or study this field in more detail, because I think while there is a huge amount of people working with wireless communication research today, the community of people working with localization, my impression is that it's smaller, but at the same time there might be more important challenges there. I mean, more room for improvement that can actually make a difference in our everyday lives. So do you have some final thoughts about if someone wants to start working in this field? What should you learn? What should you, what are the main challenges that you should try to address?
That is a very difficult question, Emil. I think definitely you should learn signal processing. I think that's really our common language between communication and localization. If you have a good basis in signal processing, you can solve nearly all problems. And I think from localization perspective, it's really important to use realistic models of channels. You cannot get away with very simplified models and have something that is reasonable and credible. And that's really the starting point for all research in both communication and localization. You need to have a good way of representing the channel.
So are we also coming to the point where we need to do more experimental research in this direction to validate that our models are good, or do we know that they are good?
Yeah, this is really something that I think will change in the future, that we have to step away from our maybe very beautiful mathematical models and kind of start facing reality and talking more to people who do circuits, antennas, who really know about the hardware and make real progress in these areas. So this is really challenging for us, but I see we have to do it.
Indeed. I think this is really the important thing now when we are doing research towards 6G, that instead of trying to rush to find the latest use cases or things like that, to really take this time now. 6G shouldn't be here until 10 years from now. So to go back and if you know signal processing, learn about the electromagnetics, or if you know electromagnetics, learn about signal processing and communication theory, or try to expand your knowledge so that these different fields can really come together and do real credible advances. So Eric, do you have any final thoughts or questions?
No, not really, more than to reiterate what I think you said, Henk, right? That learn signal processing. And indeed, I tell my students in my first lecture that learn model-based signal processing, right? Like classical detection estimation theory, for example. And learn data-driven signal processing, which means modern machine learning methods and neural networks and all that, because we need both.
Indeed, I couldn't have said better myself.
A great wrap up then. So thank you to all the listeners for staying with us all until the end. And we are very grateful to have Henk here as our guest in this episode. And yes, we will put some links in the description to this episode, where you can also find some recommended reading by Henk if you would like to know more. And with that, I would just like to thank everyone for listening and being here. Thank you.
Thank you.
Thank you.